What it says, in a survey of 607 general surgeons and orthopedic surgeons indicated their major professional activity. The results are summarized in the table above. One of the surgeons is selected at random. Which of the following is closest to the probability that the selected surgeon is an orthopedic surgeon whose indicated professional activity is research? So what we want to do is we really want to narrow down this exact individual, right? So if you look, we have their major professional activities. We have general, 258 were teaching, 156 were research, for a total of 414. And then for orthopedic surgeons, 119 were teaching and 74 were in the research field. So what it's asking is, out of this total, the total amount of surgeons, right? Because they all participated in this survey, what's the likelihood that we're going to select one that's an orthopedic that is in research? Well, the amount of orthopedic surgeons that are in research is 74. So to find this, we really just want to take 74 divided by 607. And when you do that in the calculator, you get about 1.2 or 0.1219. So we're going to round that up to get our answer of A, 0.122. Okay, not necessarily a difficult question, just makes you study a table and understand what it's saying, especially with the total rows, that's total, or the total column, it's total of each row. Okay, and then you want to focus on the specific individual. So 74 out of 607 gives you 0.122, which corresponds to the answer. All right, I know it's been a while, but now we're off onto our 5-minute check of section 4.4, 4-4. It says, describe how the graphs of f of x, which is equal to the sine of x, and g of x, which is equal to 2 sine of x, are related. Then finally, amplitude and period of g of x. So first, remember, we have our general form where it's a times the sine of bx minus c, all in parentheses, plus d. So where do we actually have numbers? We have a value of 2 in for a, and then it's just sine of x. So our value of, so we could write it like this if we really wanted to, but that's redundancy in mathematics. So we alleviate it. So if we're comparing this to just the general sine of x function. You can see that 2's been replaced. We still have a 1 for b. There's no horizontal shift. There's no vertical shift. So 2 is your amplitude factor. Remember, that is the distance from the midline. So this has been expanded vertically by a factor of 2. And then did anything change with the period? Oh, we can find that. Remember, to find the period, it is 2 pi over the absolute value of b. In this case, that is 2 pi over 1. So our period is still 2 pi. So we have an amplitude of 2 and a period of 2 pi. Now we want to select the answer that shows that. That should be C, right there. On to the next one, okay? So now we're sketching the graphs of f of x and sine of x, or f of x is equal to sine of x and g of x is equal to sine of 2x on the same coordinates. I'm not going to graph this one. We're just going to kind of analyze it. Remember that the sine function generally starts at the origin, okay, or on the midline at the y-axis, pending any vertical shifts or phase shifts or vertical shifts. But in this case, we said there wasn't any vertical shifts. So we're looking for a graph that's been expanded by a factor of 2. So let's look at A first. You can see this dotted line is sine of x, and we don't reach our maximum. Right there, this one, this dotted line, is more like 0.5 times the sine of x. Okay, whereas 2 sine of x should touch the amplitude of 2. because the y-intercept is, or the x-intercept, x-axis, blah, 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 blah. Give me a second to compose. The x-axis is our midline. So since we have a factor of 2 for the amplitude, we should be 2 units away from the x-axis. This one doesn't work. Okay, let's look at answer C. We finally got our amplitude right, but you can see that the full period is done in 4 pi, so that one doesn't fit, okay, because we're looking for one that is done in 2 pi. Let's look at D. D, y sine of x and y2 sine of x have the same amplitude, which is not correct because g of x should have the amplitude factor of 2. So from the process of elimination, that leaves us to B, but we have an amplitude of 2 from the midline of the x-axis, and it completes a full period within 2 pi. So our answer here is going to be B. Okay, state the amplitude, period, and frequency, phase shift, and vertical shift of f of x is equal to 2 sine of x plus pi fourths, pi over 4. Okay, so we have 2 sine x plus pi over 4. Okay, looking at amplitude. Once again, that's the absolute value of our value A. So in this case, that's the absolute value of 2, or 2. Okay, the period can be found by taking 2 pi divided by the absolute value of B. In this case, our value of B is 1. So our period is 2 pi over 1, or just 2 pi. There. So amplitude, period, frequency. What this is, the frequency is, frequency, remember, is the reciprocal of the period. So our period is 2 pi, our frequency is 1 over 2 pi, the reciprocal there. And then phase shift. Phase shift, we can find that by taking whatever's on the interior of our parentheses, or bx plus c, set it equal to 0. So we have x plus pi fourths, set that equal to 0 and solve for x, minus pi fourths on both sides. And we'll get that x is equal to a negative pi fourths. That means our graph has been shifted left by pi fourths, and vertical shift comes from the value D. It adjusts the midline up and down. So in this case, it's plus 0. So there is no vertical shift. So we're looking for one that has an amplitude of 2, a period of 2 pi, frequency of 2 pi, 1 over 2 pi, and a phase shift of negative pi fourths. That looks like it's going to correspond to answer A. Okay, the hard one on that is just remembering that the frequency is the reciprocal of the period. Okay, graph 2 periods of 2 sine of x plus pi fourths. So we have the same equation. So luckily, most of our stuff is already taken advantage. We already found our phase shift was negative pi fourths on this one. The only thing that I did not do to graph this, right, because I found my amplitude, I found my period, I found my phase shift. The last thing, and I found vertical translation. Remember that when we're graphing it, sine and cosine, it breaks itself down into 4 important points, or 4 critical points, right? We find these by taking what's known as the x scales, okay? X scales. And what we do is we take our period, which is 2 pi, and then we divide that by 4. In this case, we're going to get pi over 2. Okay, so what that means is the location of our critical points happen every pi halves. Okay, first I'm going to take into account my horizontal shift of of a negative pi fourths. Okay, so I moved left this way. Then to find the location of my other critical points, I'm going to add pi halves. Okay, I have to have a common denominator. So pi over 4 and negative pi over 4 plus 2 pi over 4 is what I get with the location of my critical points. Hold on. So this is going to be pi over 4. And if I add it again, I get 3 pi over 4. If I add it again, I get 5 pi over 4. If I add it again, I get 7 pi, 9 pi, 11 pi, 13 pi. And that should be the location of all my critical points. Adjust my amplitude to 2. That's a negative. And then proceed to graph it. So I start here, then I go to the maximum because it's the sine function. Then I go back to the midline. Then I go to a minimum. Then I go back to the midline. Then I have a maximum, midline, minimum, and I finish up my period at 15 pi over 4. Finish it off with a gentle curve. Like such. And just remember that our period is there. And there. So it started at a negative pi fourths. Critical point number 1 is the maximum because it's the sine function. Okay. Critical point number 2 is back to the midline, sine function again, then to the minimum value, then back to the midline, and repeat that process to complete your periods. Comparing it to the graphs, looks like this one should be answer C again. As you can see, I started here, had my critical point max, then back to the midline down. I don't like how they do their scales because it can't really tell you. But you can see I should be at my minimum just over pi, which is at 5 pi over 4 on my graph. I hate the way they do their X scale there because it doesn't show you the location of it. All right. Next one, it says write a sinusoidal function that can be used to model the initial behavior of the sound wave with a frequency of 0.82 hertz and an amplitude of 0.35 or 820 hertz. So this one requires us to use the period. Okay, remember that on our sine functions, we can find the period by taking 2 pi divided by the absolute value of b. Okay, and they give you the frequency, which is the reciprocal of this. So if I put 1 over 820, that is my period, right? But I'm trying to find the value of b. So if I cross multiply, b times 1, 2 pi times 820, you'll see that b is equal to 1640 pi. Okay, cross multiply and divide. And then the amplitude, it says with 0.35. So the luxury of our sine functions, the amplitude comes from the absolute value of a. Okay, so we have an amplitude of 0.35. And they want it as a sine function. So we would write it as 0.35 sine of 1640 pi x, or pi t in this case, because our input is a value of time. All right. So we did analyze graphs of trigonomic functions. We focused mainly on cosine and sine. Okay, we talked about all the translations, all the transformations that could happen to them. But today what we're talking about is we're talking of tangent and reciprocal functions. Okay, the reciprocal functions being secant, cosecant, and cotangent. But we're not going to talk about trigonomic functions and damping factors or any of this damping stuff. What that more or less does is it puts a function in for your value of a. So it's like x squared, and it makes your graph kind of start out real low in amplitude, but as your function of x squared gets bigger and bigger and bigger, it just increases. All it is it's an amplitude transformation. Okay, and the graph of the sine will follow where the amplitude is at. Okay, it's nothing too terribly difficult. But we need to nail down the tangent and our reciprocal functions because those are more key. Okay, so properties of the tangent function. So as we know, tangent can become undefined. Okay, and before we even really get into that, if we go back to our unit circle here, where we have this point is 1, 0, this point is 0, 1, negative 1, 0, 0, negative 1. And if you remember, tangent is equal to y over x. Okay, tangent of theta. Tangent of theta is equal to y over x. What this sets up is that our quadrantal angles are either going to be 0 or undefined. Okay, so like this point right here, tangent of 0 degrees, tangent of 360 degrees. That is 0 over 1 or just 0. So tangent of pi halves is equal to y over x. You can see that it's 1 over 0, which is undefined. Okay, what this does is it means that you're going to have vertical asymptotes. Okay, when you're graphing this function and the cotangent function. Your vertical asymptotes happen every time you touch the y-axis. Okay, in terms of rotating the terminal side. So if we're looking at this, we'd have pi halves. We'd have 3 pi over 2. Okay, and then we would have, what is that, 5 pi over 2? 5 pi over 2, 7 pi over 2, 9 pi over 2, and 11 pi over 2. Okay, all of these angles are coterminal and fall upon the y-axis. These are situations where you're undefined. Okay, in between there, like 0 and 2 pi, you have where tangent is 0. Okay, you also have it at negative or at pi and 3 pi are your y-intercepts. Okay, and what it sets up is a graph that kind of starts low, ends high, and has asymptotes on both sides. Okay, also something that's different with the tangent function is that it completes a full period within pi. Okay, not 2 pi. We don't have to go all the way around. A full period occurs every pi radians. Okay, so the period is half as short as sine and cosine. Okay, so just some small differences. And if you were to look when we're going this way, if I draw up my letters, okay, going from 0 all the way until 90, tangent is going to hit positive. Then we hit 90. Then we start a negative aspect. Then we have our intercept. then we're positive again, then we have an asymptote, then we're negative again, intercept, positive, and it repeats itself. It repeats itself every pi radians, and you can kind of see it on this graph or on this chart here. So starting here, this would be 0. You can see that we're positive, where all trig functions are positive. Then we hit the positive y-axis at pi halves. That's our asymptote. And then we're negative, and we work ourselves all the way up till pi. And then we're positive again in the third quadrant. Then we have an asymptote. Then we'd be negative until we reach 2 pi, where we'd have our next intercept. And then we'd be positive until we have our next asymptote at 5 pi over 2. Okay? So you can see it's a periodic function, but where we're trying to find, or what we're trying to focus on, is asymptotes and intercepts. Okay, that's how we graph this. You have asymptotes and intercepts. They bring in what's known as the intermediate point, which is at pi fourths radians, and that's where you intersect at 1. Okay, but these are just sketches of these graphs. So we're going to kind of compress them. You can't really stretch a tangent function because it's unbounded. The closer and closer you get to the these asymptotes, our graph goes farther and farther positive or farther and farther negative. Okay, and that's simply because we're taking y divided by x. So in this case, you can see our x value is getting smaller and smaller and smaller because we're rotating where we're getting closer and closer to the y-axis. And you can see it just kind of goes off to infinity. So the range on a tangent function is negative infinity to positive infinity. You can see the domain is all real numbers where x cannot equal pi halves within pi. So it starts at pi halves, then every pi rotation, we have another asymptote. Okay, the y-intercept is 0. The x-intercepts occur every pi radians. Okay, and this is also based upon the damping factor. Okay, we have an infinite discontinuity at pi halves and negative pi halves. The asymptotes correspond to the infinite discontinuity. The symmetry is an odd function, so if we rotated it about the y-axis or about the origin, we would map upon each other. And the end behavior is the limit as x approaches negative infinity. Tangent and x do not exist because the function oscillates between negative infinity and positive infinity. Okay, the key things that you really want to draw from it is that the function starts low, it ends high. The x-intercepts occur every pi. Okay, and our asymptotes are every negative pi halves and pi halves, or every pi halves, however you want to look at it. So we really graph this by finding x-intercepts and asymptotes. Okay, if we can do that, we're in a good spot. Okay, the period of the tangent function is the distance between any two consecutive vertical asymptotes. So right here and right here. And the period can be found by taking pi divided by the absolute value of b. So it's the same type of calculation we did in sine and cosine, but instead of using 2 pi, the period of tangent happens every pi radians. Okay, so the asymptotes are pi radians apart, and the x-intercepts are pi radians apart as well. All right, so let's graph one. So locate the vertical asymptotes and stretch the graph of y equals the tangent of x divided by 3, or x over 3. So remember, there's no amplitude factor in tangent. So we're dealing with tangent x over 3. So in all reality, we're really dealing with tangent of 1/3 times x. So to find our period, we're going to take pi divided by 1/3. Okay, anytime you have to divide by a fraction, remember you flip to the reciprocal and multiply. Okay, so really, this is equivalent to pi times 3/1 or 3 pi. Okay, that's the distance between our asymptotes and our intercepts. Okay, on this graph, we can find out where our first x-intercept is very easily. Okay, and you find the x-intercept the same way that we found the phase shift for sine and cosine. Okay, so the first thing, x-intercepts. So if we take what's on the inside here, so x plus 0, because our value of c is 0, and we set that equal to 0, you can see that I'm going to minus 0 from both sides. I'm going to be left with x over 3 is equal to 0, and then I'd multiply by 3 to isolate x, and you'd see that x is equal to 0. This is the location of my first intercept. Okay, that's at the origin. It's the first one. The next one happens 3 pi radians away. Okay, so that means I have an x-intercept at 3 pi, 6 pi, and negative 3 pi. Okay, I'm just finding locations of them. I'm going to put those up in the top right corner. Okay, x-intercepts found the same way that we did with the phase shift for cosine and sine. Taking whatever's in the inside, set it equal to 0, and then solve. Okay? Our asymptotes, they originally occur at negative pi halves and pi halves on the parent function. So what we're going to do is we're going to set bx plus c, once again, equal to these, and we're going to be able to solve, and that's going to give us the location of our new asymptotes. So my value of b was 1/3, my value of c is 0. So I have x over 3 plus 0 set equal to positive pi halves. Subtract 0 from both sides. X over 3 is equal to pi halves times 3 on both sides, and I get that x is equal to 3 pi halves. This is the first asymptote. Right there. Going to the positive side, because it was set equal here. Okay, this one. We're going to do the same thing. X over 3 plus 0 set equal to a negative pi halves, and then we're going to solve for x. So subtract 0 on both sides, and then multiply by 3. We're going to get that x is equal to a negative 3 pi halves. Okay, this is the first asymptote on the negative side. So I'm going to make note of that. Asymptotes at 3 pi halves and negative 3 pi halves. And now I can actually stretch my graph. Okay, I have the location of my intercepts, and I have the location of my asymptotes. So starting with here, and I'll just label it in red. Okay, my first was there, my first asymptote is at 3 pi halves. My negative asymptote, the negative 3 pi halves. Okay, and I'll do my graph here. So my first intercept was there. My period I found was at 3 pi. That means I have another intercept there. I have another intercept here. Draw my asymptotes first. Okay, now I just know how my function acts. It starts slow. Comes through the x-axis, finishes high. Okay, on this side, I'll just draw it there. And on this side, it's going to look like that. Okay, I could finish it off, but the graph says to sketch it, and I can sketch it by 2 consecutive asymptotes. So the period is pi over 1/3, or 3 pi. Then find 2 consecutive vertical asymptotes by solving bx plus c is equal to a negative pi halves, and bx plus c is equal to pi halves. Remember, on the parent function, this was the original 2 asymptotes. And what I mean by that is those are right here, negative pi halves and pi halves. Those were the original ones. And since bx plus c corresponds to phase shifts, if we set those equal to it, we're going to be able to find the location of these other asymptotes, right? Because we have the original ones, and then we can just add the period to it. Okay? They simplify. So this is the negative asymptote with 3 pi, negative 3 pi over 2. Here's the first positive asymptote at 3 pi over 2. Okay, they create a table. We're only concerned with vertical asymptotes and x-intercepts. Okay, you can see the intercept hasn't moved. So right here is the first intercepts. And then if you pay attention, our x-intercept occurs every 3 pi. Okay, and we have a new asymptote every 3 pi. I didn't carry it out here. This is 9 pi over 2. But if I were to have, what I would have done is I would have taken 3 pi over 2, the location of this one, and I'd add 3 pi to it. 3 pi over 2, and I want to add 3 pi. So first, I got to find a common denominator. So I'd multiply each by 2 to get that I'm really adding 6 pi over 2. So 3 pi over 2 plus 6 pi over 2 is equal to 9 pi over 2. And then the same thing would happen on the negative side. But I would end up at a negative 9 pi over 2. Okay, so that's how they found the location of these other asymptotes. So, but the real key is, since we know the period, right, by taking pi divided by the absolute value of b, we know how long it takes for it to complete one cycle. We find the x-intercept, the original one, to determine if it's been shifted left or right, and then we can add the period to find the next x-intercepts. Okay, and then we take bx plus c, set it equal to the original asymptotes of pi halves and negative pi halves, and that corresponds with the shift as well, right? Because it's all either going to shift left or shift right or stay centered. But then from there, if we add the period again, we can figure out how far it is between these distances. So from here, this is 3 pi radians. 3 pi radians, 3 pi radians. From the x-intercept, 3 pi radians, 3 pi radians. So really it's centered around finding the period and then sketching our graph, and to use those to find our other asymptotes as well. Okay, so locate the vertical asymptotes of y equals the tangent of 4x. So remember, what we want to do, and we can find a whole bunch of them. We'll find a whole bunch of them. So I have tangent of 4x. Okay, first thing that I want to do is I just want to find my period. How long does it take it to repeat itself? So period is found by taking pi divided by the absolute value of b. My value of b is 4 here. So that is equal to pi divided by 4. Right? That's how long it takes to repeat itself. Okay, where's the location of my first asymptotes? Well, I take bx plus c. So right now it's 4x plus 0 because I don't have a value for c. I set that equal to a negative pi halves. And I'm going to solve for x. Then I take bx plus c. Once again, it's 4x plus 0. And I'm going to set that equal to pi halves. Right? And I'm going to solve that, and this is the location of my asymptotes. So I'm going to add 0 or subtract 0 from both sides. I'm left with 4x is equal to a negative pi halves. And then I divide by 4 on both sides, which will give me negative pi over 8. Okay, on this side, subtract 0 from both sides. 4x is equal to pi over 2 divided by 4 on both sides, and I get x is equal pi over 8. Okay, so these are the locations of my first two, but you can see the first ones occurred at pi eighths, and then they're going to occur every pi fourth. Okay, so we'd add that to them, and that would get to 2 pi eighths. So that's like 3. That'd be negative 3 pi over 8 after I make the conversion, because that's 2 pi over 8 to equal it. And then the next one would be at 3 pi over 8. And then it would be 5 pi. Okay, a simple algebraic way to say that is right there. The vertical asymptotes occurred at n pi eighths. So where n is an odd integer. Okay, so what that means is that it went from 1, so pi over 8, then it went to 3 pi over 8, then it's going to go to 5 pi over 8, then it's 7 pi and 9 pi in both the negative and positive x and y, or x-axis. So you can see tangent, it has quite a few similarities to sine and cosine, but it's not the most difficult thing. So sketching the graph of y equals tangent of 4x. So we've already found this. Okay, the only thing that I didn't do so far, I found my asymptotes, right? Because that was what the first question asked. Where do your asymptotes fall? Well, we said that they're at negative pi eighths. Then the next negative one is negative 3 pi eighths. On the positive side is pi eighths and 3 pi eighths. But the only thing I didn't do was find the x-intercept. So we have our asymptotes taken care of, because that was off of the first question. So, but let's look at our intercepts. So the intercepts is found the exact same way as if we take bx plus c, 0 in the case, and set it equal to 0. So I have 4x plus 0, set equal to 0, solve for x, and you get that 4x is equal to 0, divide by 4, and you'll get that x is equal to 0. So our period was pi over 8, right? Every pi eighth. So that means we have an x-intercept at 0, pi eighths. Then it'll be 2 pi eighths or pi fourths. Then it'll be 4 pi eighths. Okay, on the negative side, starts at negative pi eighths, a negative 2 pi eighths, and it continues and continues and continues. So there will be an even. And if we take that information of our intercepts and our asymptotes, we can put them to find our graph. We had an intercept at 0, which we found, and then they're every pi fourths, because our period was pi fourths. I guess on my calculation, I added pi fourths, but I did it by just using it as 2 pi over 8 rather than simplifying it. So 0 here, 0 at pi fourths, which is what we found from our period. So remember, the key to graphing tangent is first, find your period, find the locations of those asymptotes, find the intercepts, and then sketch it. So here we have the graph of a negative tangent x over 4. Okay, locate the vertical asymptotes and sketch it. All right. So what does this do? What does the negative out front do? Well, it flips it over the y-axis or the x-axis. So instead of starting low and finishing high, our graph now is going to start high and finish low. Okay, it's a reflection over the x-axis, this negative. We have a period factor of 1/4. We have no element of C, the altitude didn't change, and we didn't have a vertical transformation at all. So how can we do this? First, as always, we want to find the period. So the period is pi over the absolute value of B. In this case, that is pi over 1/4, because it's x over 4th, or 1/4 times x, however you want to look at it. And that is equal to 4 pi. Okay, once you take care of that, we want to find the location of our x-intercepts. So we're going to take 1/4 x plus 0, set that equal to 0. Subtract 0 from both sides, we get 1/4 x is equal to 0, multiply by 4 on both sides, and we get that x is equal to 0. Okay, so this is our first one. We know it starts at the origin, and then it reoccurs every 4 pi. Okay, asymptotes. We find the first negative and the first positive by taking bx plus c, set it equal to a negative pi halves. So that's x over 4 plus 0 equal to a negative pi halves. Okay, and then we solve, subtract 0 on both sides, get x over 4 is equal to a negative pi halves. Multiply by 4. That's going to give me x is equal to a negative 4 pi over 2, or negative 2 pi. Yep. Okay, do the same thing with our positive side. So setting it equal to a positive pi halves, solve for x. Multiply by 4 on both sides, and get that x is equal to 4 pi over 2, or 2 pi. So this is the critical information. Okay, I've got it boxed. My first x-intercept is 0, okay, or at the origin. My first asymptotes are at negative 2 pi and 2 pi. So I take that information and I graph it, negative 2 pi and 2 pi. Remember that Mr. Burns still messed up. Negative 2 pi and 2 pi. So I draw my XY graph here. So 2 pi, I have an asymptote. At negative 2 pi, I have an asymptote. Okay, and then I could add my period to this. So if I count by just 4s, or just by 2 pi, I go to 4 pi, and then I go to 6 pi, which is the location of my next asymptote. 4 pi, 2 pi plus 4 pi is 6 pi. Do the same thing here. A negative 4 pi, negative 6 pi. Okay, so this is what my graph looks like so far. But remember, it had a negative for an A value, so that corresponds to flipping my graph over the x-axis. So instead of starting low, it's going to start high and finish low. Just like that. I'm pretty good at this stuff. That's them finding their vertical asymptotes at negative 2 pi and pi. They found the period is 4 pi. And there we go. Okay. Last one that we're doing on tangent, because we got to cover the other sinusoidal functions. Actually, we're going to just get to the other reciprocal functions. We're not going to do that one. This one, if you're looking at it, it's going to flip y over x. It's going to have a shift left. So instead of our first two asymptotes being at negative pi halves and pi halves, it's going to be at negative pi and 0, because that's once we set what's on the interior there, set equal to 0. You can see that once we minus pi halves to a negative pi halves, that gives you pi, and then pi halves minus pi halves gives you 0. So our period didn't change, it's still pi. Here they're finding their asymptotes. See, it's at negative pi and 0. And once again, that's from setting bx plus c equal to a negative pi halves and pi halves. Okay, they would have found the intercept, the first one, which would be negative pi halves, because this has been shifted left. Okay, it's the same process. Okay, properties of cotangent function. Okay, so you can see the tangent function and the cotangent function are very similar to each other. Okay, cotangent kind of looks like a negative tangent, which it is, but the key difference is where our intercepts and our asymptotes occur. Okay, so if tangent is y over x, cotangent is x over y. So every time we would rotate a terminal side and hit the x-axis, we have an undefined point. So like at 0 and pi and 2 pi and 3 pi, every time we're bouncing back and forth on the x-axis for an angle in standard position. What I'm talking about is right here. Okay, using the same points that we did with tangent. So cotangent of theta is equal to x over y. Okay, because it's the reciprocal of tangent, which is y over x. So here on 0 and pi and 2 pi and 3 pi and so on, we have the locations of our asymptotes. Okay, these are asymptotes, whereas with tangent, it was our y-axis. Okay, so these are undefined points. These are our intercepts. Okay, we can handle it the same way that we handle tangent. We'll find the location of our first intercepts by, instead of setting it equal to pi halves and negative pi halves, we'll set it equal to 0 in terms of our interior stuff. Okay, and sketching graph of tangent, of cotangent. Okay, other similarities between these two is, once again, the period is pi. Okay, still the range is all real numbers. The domain asymptotes can equal pi's. Okay, infinite discontinuity. It's an origin. It is an odd function. Okay, if you rotated 180 degrees, it would map upon itself. No extrema, and the limits do not exist for end behavior. Okay, so locate the vertical asymptotes and sketch the graph of cotangent of 2x. Okay, so the first thing we're going to do, like always, is we're going to find our period by taking pi over the absolute value of b. So in this case, the period is pi halves. And we want to find two consecutive vertical asymptotes. So we set the interior bx plus c, we set it equal to 0. Okay. Honestly, you could treat these as graphing the tangent function. It's just kind of flipped a little bit, because the asymptotes of the cotangent function are the x-intercepts of the tangent function, and vice versa. Okay, so with tangent, we set bx plus c equal to pi halves and negative pi halves. In cotangent, we set that equal to 0. Well, that's how we found the x-intercepts of tangent, right? So we're doing the same thing. We're just doing it a little different. Okay, so in this case, how would we want to find our x-intercepts for cotangent? Well, we'd set it equal to negative pi halves and pi halves. Okay, so in this case, we said we're finding our asymptotes. Okay, they set it equal to 0 and pi. Okay, and you can see 0 and pi. You can also set it to 0 and then just add the period on both sides. Like 0 plus pi halves, 0 minus pi halves. And then they found the intercepts right there. Okay, so it's really the same process with tangent and cotangent. It's just remembering that the cotangent asymptotes are the tangent intercepts. Okay, so locating the vertical asymptotes of y equals 1/2 cotangent of 2x. So now we have a value of a that doesn't affect us at all. So we would set 2x plus 0 equal to 0 and pi, and we would get that they are going to be, should be b. There. That x is equal to n pi halves, and n is an integer. So for every pi halves, the period repeats, we get a vertical asymptote. Okay, I'm trying to rush because I got to get to secant and cosecant. But cotangent and tangent, they follow pretty well. Okay, So here we go. This is the big one because I got 30 minutes left. We're going to spend it. So the book's method on graphing these functions is a little bit different than mine. Okay, what I do to graph a secant or cosecant function is I feel comfortable with sine and cosine. So really, I'm going to graph my sine and cosine function. That way, I can find my x-intercepts, and then I'm able to draw my asymptotes. The same way that tangent and cotangent, or the same way that tangent. Here, I got to write this. So tangents. The graph of tangent, right? Their x-intercepts equal the asymptotes of cotangent, right? That's because that tangent was y over x, and cotangent is x over y. So the same thing happens here. So when we take the sine function and we find their x-intercepts, that's the asymptotes of cosecant. Okay, and then once we take the cosine x-intercepts, those equal the asymptotes of secant. So really when I'm graphing cosecant and secant, I'm really just graphing sine and cosine. I'm going to do the exact same things over and over again, but it's not going to be, it's only to find the locations of my asymptotes. So if I bring you back to the parent functions of them, here we have cosecant, which is a reciprocal of sine. So we know that sine starts on the midline here, right? And it increases to 1 and then decreases to -1. You can see that sine would have an x-intercept here at 0, and then it would have one at pi, and then it would have one at 2 pi. But those are our asymptotes, okay? And really, our sine function comes up like this and goes down, and then it's really just that flipped, okay? So the range of our secant function, it's never going to be less than -1, or it's never going to be more than -1, and it's never going to be less than 1, because those are our amplitudes. Okay, so the amplitude still applies here. It has no y or x-intercepts, okay, because it has the asymptotes. Okay, it has an infinite discontinuity at every pi radians, so that's pi, 2 pi, or every time that sine would be 0. Okay, it is an odd function. If we were to rotate it 180 degrees, it would map upon itself. Okay, everything's similar to sine, and the end behavior doesn't exist. So if we're looking at the secant function here, which is the reciprocal of cosine, see the range once again is cut off. It doesn't have anything between -1 and 1. It's all outside of it. There are no x-intercepts. There's one y-intercept. Okay, and that's at 1, unless it's been expanded amplitude-wise. Infinite discontinuity at y equals pi halves plus n, so every pi halves, or whenever cosine would be have an x-intercept. It has y-axis symmetry the same way that cosine does. Okay, so really we're graphing the same stuff. I'm going to show you how it kind of works. The book's method is a little bit different. It kind of complicates it a little bit harder. Okay, so locate the vertical asymptotes and sketch the graph of y equals the negative secant of 2x. Okay, and I'm going to treat this exactly like I'm graphing a cosine. Okay, And that's what I'm doing, because the input secant and cosecant into a graphing calculator, you literally have to put 1 over cosine. So this is what we're really graphing. Negative 1 over the cosine of 2x. Okay, that's legitimately what we're graphing. We just call that a negative secant of 2x because it's the reciprocal. Okay, so when we're talking, we'd always go amplitude, right, period, x scales, phase shift, and vertical transformation. And I'm approaching this like I'm graphing cosine. So it's negative 1 over it. So what's my amplitude? Well, my amplitude is still 1. So it's still the absolute value of 1 there. So my amplitude is going to be 1. My period, once again, is found by taking 2 pi divided by the absolute value of b. My absolute value of b is 2. So in this case, it's 2 pi over 2, or pi. Right? My x scales was found by taking my period divided by 4. So my period is pi. If I divide that by 4, I get pi over 4. Okay, my phase shift, taking bx plus c, setting it equal to 0. So I have 2x plus 0 set equal to 0. So that's minus 0 on both sides. It's 2x is equal to 0. X is equal to 0, so there's no phase shift, and there's no vertical translation. Okay, the only thing I really got to pay attention to is the negative in this case. So if I start to draw my cosine graph, you'll kind of see how it maps onto us. So my amplitude was still 1 to negative 1. So I have 1 there. I have negative 1 here. Okay, my phase shift was 0. However, it's a negative. So it's flipped over the x-axis. Right? So instead of starting here for cosine, I'm going to start here. Okay, the locations on my x scales was every pi fourths. Okay, so 0 plus pi fourths is pi fourths. And then it would be 2 pi fourths, or pi halves. Then it would be 3 pi fourths. Then it would be pi. Then it would be 5 pi fourths to 6 pi fourths. Label my other side. I know my scale's a little small. I'm sorry. But what I've done, my x scales were pi fourths, so I just added pi fourths from my origin, from my starting point, because my phase shift was 0. Okay, well, cosine, it starts at the altitude, or starts at its amplitude, and then it goes towards its x-intercept. So I'm going to dash what I think a cosine graph would look like. Okay, and I'm going to draw it just like that. And you can see the dashes. This is what my cosine graph would look like. Okay, the period was pi. Okay, so every pi hit. And why I want to do this is because where these x-intercepts are, those are the asymptotes of my secant graph. So you can see my asymptotes here in purple. Right, you can kind of see my asymptotes. Those correspond to my intercepts of what would have been my cosine graph. So now I know that secant always intersects cosine and sine at the amplitude of each function, okay, meaning that they intersect at 1. So in this case, cosine and secant would intersect at 0, -1. And then my graph is just like this. I just finish off graphing. Looks like little parabolas. It might be better if I show you this on decimals. Okay, and the purple would be my cosecant or my secant graph. Okay, I'm going to try to show you that on decimals real quick. Let me open it up. Give me another one. Okay. Because I don't know if you can really see my stuff. Stay on that side. Bring me here, take me to decimals. Okay, so the first graph that I'm going to graph is a cosine. So functions, cosine of 2x. Okay, you can see that. This was, oh, I'm going to put negative out in front because we had a negative. You can see that it just flipped it over the axis, right? So this is what I used to graph the secant, because secant's the reciprocal, and if you want to use a graphing calculator, you really have to put it in like this, as 1 divided by the cosine of 2x. And look at this. So the maximums of what correspond to a cosine, like if we're just looking on the positive side of the x-axis here for the y-axis, you can see our maximums become the minimums. This is where we're intersecting. Okay, so this point right there is pi halves to 1. On my graph, I have this 2 pi over 4, but you can see it's still there. So, and then it's 3 pi, and then 5 pi. Okay, on the negative side, what would be the minimums of our cosine graph are now maximums of our secant graph. Okay, the intercepts of my cosine graph, the intercepts are now the asymptotes of my secant graph. Okay, so really when I'm graphing secant and cosecant, I'm approaching it like I'm graphing sine, okay, or cosine. And then I just got to remember how it actually breaks down. Okay, if that makes any sense. These are two of the graphs lined up to each other. This is what I tried to do in the dotted red, and the cosecant graph is the purple on my board. Okay, so cosine was dotted red, purple was the secant graph. Okay, so you can see that the intercepts really cause the asymptotes. So we can do these pretty quickly and simply if we're just thinking that we're graphing sine and cosine. But the book's method, they make it a little bit more difficult. Okay, is the graph of y equals secant x compressed horizontally, then reflected in the x-axis. The period is 2 pi over the absolute value of b, so that's the exact same as, and then the asymptotes occur when bx plus c are equal to negative pi halves and pi halves, which that's the part that I don't really like. They approach it like you're graphing a tangent or a cotangent, when in all reality, it's much easier if you look at it as graphing sine and cosine. Okay, we can treat it the exact same way by finding our x scales and then just knowing, hey, cosine starts at its amplitude, then it goes to its intercepts. Sine starts on its intercepts and then goes to its amplitude. So we don't really have to overcomplicate it this way, the way that they do. Okay, so here's a cosecant one. Okay, I'm going to handle it the same way that I handled that cosine graph. Okay, so it's cosecant, or the way that I handled that secant graph. So it's cosecant of x plus pi thirds, right? Okay. So in all reality, what that is it's 1 over the sine of x plus pi thirds. Okay, that's really what we're dealing with. Okay, the amplitude still at the absolute value of 1. So I know that my minimum and maximum values for cosecant are going to occur at like 1. Okay, the period, 2 pi divided by the absolute value of b. Our value of b is 1, so the period is still 2 pi. Okay, the x scales. I take 2 pi divided by 4. I get pi halves. That means that every pi half, I have a critical point. I have an x-intercept or a maximum. The phase shift, taking bx plus c, set it equal to 0. So x plus pi thirds, set equal to 0, and solve for x. We get that x is equal to a negative pi thirds. Okay, the vertical translation, there is none. Okay, so I draw my graph, my xy. Okay, and the first thing I want to take care of is my vertical shift, or my phase shift, which was a negative pi thirds. Okay, that's where my sine graph starts. Now to find my x scales, okay, I take negative pi thirds and I add pi halves to it. So I've got to find a common denominator, so negative pi thirds. I want to add pi halves, so that's going to be sixths. That's negative 2 pi over 6. And I'm going to be adding 3 pi over 6. Those are my common denominators, okay? I had to multiply this one by 2, I had to multiply this one by 3. So negative pi thirds is really negative 2 pi over 6, and pi halves is 3 pi over 6. That way I have common denominator, I can add. So the next one is at pi over 6. Okay, the next one after that, I add 3 pi over 6, that's going to be 4 pi over 6. The next one after that, 7 pi over 6. Next one after that is 10 pi over 6. Next one after that is going to be 13 pi over 6. This one going negative side is going to go negative 4 pi. Oh, can't do that one just yet. Negative pi thirds. So that's going to be negative 5 pi over 6. Negative 8. Negative 8 pi over 6. Okay, that should be plenty of. Okay, finish off my amplitude state at 1. So I'm between 1 and negative 1. And like I said, I'm starting to just dash my sine graph. So I have a maximum there. Then I have an intercept. Then to my minimum, be there. Then I have an intercept. Then to my maximum there. So that's kind of what my sine graph is going to look like. And why do I care about what my sine graph looks like? Well, I didn't even really prove 2 full periods, but it's okay. Because my x-intercepts on my sine are my asymptotes. Okay, so now I can take this Just approach both apps. So really, it's much easier if we approach it as graphing these as our sine and cosine functions, rather than trying to locate them as tangent. I think it's more consistent that way. So if we're just looking at it, it was sine functions, sine, oh, let me get rid of that one. Sine of x plus pi thirds plus pi divided by 3. Right there. Bang. With it starting at negative pi thirds. That's what I graphed in red as kind of my guiding function, you could call it. And you can see how they overlap. My sine is in red, so I just started with my x scales. Right there was negative pi thirds. Then I had my maximum pi 6, then 4 pi over 6, and 7 pi over 6, 5 pi over 3. It's because I didn't simplify mine. I just left them as improper fractions. But I found all of these critical points for my sine function because that led me to my secant or my cosecant function. Okay, if I remember, I always intersect at what would be a maximum or a minimum on the sine function, because those are going to be maximum and minimums in my cosecant function as well. All the phase shift stays the same. The period stays the same. The only thing that would change is if we had a vertical translation. But you can see it'll handle it the same way. So if I did it like +3 here, or +5, and brought that up, and then I put +5. So you can see even with the vertical transformations, it's the same graph. Or it's not the same graph, I'm just using the same key points. Here we just got to find our midline first, which is there. It's nice when it has the x-intercept for the x-axis. Okay, so that is your homework, or that is what you're covering. You're graphing secant, cosecants, tangents, and cotangents. I have like 7 minutes left, so I think all your homework comes from page 277. It needs to be done by Wednesday at 8. If you have any questions tomorrow, I won't be available after school today because I have basketball, but I'll be able to help you tomorrow during the day. Also, parent-teacher conferences. If your parents want to talk to me, I have a sign-up genius that is on the school website, and I will be available Wednesday. Wednesday is my big day because Thursday we have basketball again. Or if your parents want to talk, they can always shoot me an email. I'll set up a time to go over it with them.